Differentials can be used to make little approximations, possibly even in your head. So that's often problems like approximate 4.01 cubed. You might say, well, 0.01 is pretty small. I'm going to say this is a pretty easy approximation. 4 cubed is 64, so 4.01 is approximately 64. 4.01 cubed is approximately 64. So the actual would be slightly above 64. So the actual value of 4.01 cubed is slightly above 64. And that's a great way of thinking. I applaud that way of thinking. What if we wanted to be slightly more accurate? In Calc 2, you'd actually see that this kind of thinking is called a zeroth-order approximation, which is great. Let's do a first-order approximation. You could think, what's really going on here? What kind of function are we talking about? Well, apparently cubing is what we're doing, right? So y equals x cubed is really what's going on here. And then we could say we changed 4 by a tiny bit. How much should the answer change? Well, that's what our differentials help us figure out. So dy would be x cubed prime times dx, or 3x squared dx. What should we use as x in this problem? Or you could think of it as c. Well, 4 is something easy to do in our heads, so let's use that. Or we could call it c equals 4. And then what would we use for dx? Well, it's however much change we need to get to the actual value that we want, so 0.01. So dy would be 3 times 4 squared times 0.01, which is 3 times 16 times 0.01, which is 0.48. So do we think that 4.01 cubed is 0.48? Well, that's the approximate change, but we need to add it to what the original function value would have been at the x value we started at. So 4.01 cubed should be roughly equal to 64 plus 0.48, which is 64.48. And we can think of this, what is 64 here? It's f of c. And what is 0.48? It's dy. Or we could call it f of c plus f prime at c times x minus c, where x minus c was 0.01. It's interesting to see how close this is to the true answer. So that's easy enough to type in on a calculator, of course. 4.01 cubed is 64.481201. Or you could really think of it as 64.481 instead of 0.480, so reasonably close. All right, let's do another interesting problem. Let's talk about reliability. If someone said they had a computer system that was 99.9% reliable every day, would you say that's pretty good? What's the chance it's operating for a whole year? So let's say a system is 99.9% reliable each day. What's the chance that system works every day for an entire year straight? For 365 days. Well, if you've taken a probability class, you might remember we need it to do the computation easily. We need it to be independent from day to day, that if it's operating today, that doesn't change the probability that it's operating tomorrow, which is probably not true, but it's a horrendous calculation if it's not true. So let's just do the simple, easy approximate thing and pretend it is true. So we're going to assume that the system is independent from day to day. If you don't want to assume that, come take Math 419 with me. So what we'd have is the year-long reliability would be 0.999 to the 365. I need it to operate today and tomorrow and the next day, every day for 365 days in a row. So what is 0.999 to the 365? Is that still pretty reliable? I mean, it gets slightly smaller each time because we're not multiplying by 1 each time, we're multiplying by something slightly less than 1. But it's still only slightly less than 1. What can we approximate the overall reliability for 365 days? Well, what's really going on in this question, in the previous question it was y equals x cubed. Now we're thinking y equals x to the 365. So what would we use for x there? Well, we could also compute dy equals 365 times x to the 364 times dx. Before we had 4.01, and we said, well, let's use x equals 4 or c equals 4 and dx equals 0.01, and because 4 was easy. Is there something that's easy to raise to the 365? Well, I wouldn't want to go down to like 0.99 or 0.98 or 0.90 because those are still hard to raise to the 365. What I would do here is say, well, 1 is really easy to raise to the 365. So I'd say use x or c equals 1. And then how do I get from 1 to 0.999? I'd say dx equals 1 minus, 0.999 minus 1, which is negative 0.001. So we want to use x to be some kind of value that's easy to compute with, and then dx gets us from x to the x value we really need, and it can be negative. So then we'd say dy equals 365 times 1 to the 364. I can do that in my head. And then times negative 0.001. So we get 365 times 1 times negative 0.001, or negative 0.365. So is that the reliability? Well, that's the change in the reliability from a reliability of 1. So our new y is 1 to the 365 minus, or plus, minus 0.365, which all works out to 0.365, yeah, which works out to 0.635. So is that good enough reliability? This 99.9% reliable system, what's the chance it operates every day for a year straight? Only 63%. So if it's something not very important, maybe that's okay if you can tolerate a one-day outage every now and then. But if it's something really, really important, like me watching kitten videos on YouTube or something, then it better be a lot more than 99.9% reliable. Something like bridges, airplanes, nuclear power plants, we would hope for higher reliability per day, so the final number ends up reasonable. You might say, well, I have a calculator. I can calculate 0.999 to the 365. And what does that turn out to be? It's 0.694-ish. So that's a pretty good approximation there. Let's go back and ask, what if the system was 99.5% reliable every day? So go ahead and do the calculations again and see what you get, and maybe it won't make sense, and that's okay, that's why I'm asking it. So what you would really want to do is 0.995 to the 365. You could say x equals 1, dx equals 0.995 minus 1, which is negative 0.005. Then you'd say dy equals 365 times 1 to the 364 times negative 0.005. And if you do all that arithmetic, you get negative 1.8-ish. So our estimated new y would be 1 to the 365 plus negative 1.8-ish, which would be negative 0.8, or negative 80% reliability. What do you think? doesn't seem reasonable, right? Reliability should be between 0 and 1. So that's nonsense. So what happened there? All the calculations were fine, but x to the 365 gets really, really steeply vertical near 1. Not exactly vertical, but pretty close. And the tangent line is very, very steep. So going just a little ways on the tangent line puts you back here in negative territory. So differentials are great as long as you're using them with small delta x's. And what does small mean? Well, it depends on how quickly the function is changing. And here the function was changing just so quickly that even a 0.005 delta x was too big to give us reasonable answers. Up here, I wanted to mention another way we could have done this. We could have said x equals 5, because 5 cubed isn't hard to do in your head. And what would dx be then? It would be 4.01 minus 5, which would be negative 0.99. And we could do all the same math. Which one do you think would give you a better approximation of 4.01 cubed? Using 4 and dx equals 0.01, or using x equals 5 and dx equals negative 0.99? Well, this is a much bigger dx, and usually our approximations are better when dx is small. So this is probably a worse approximation. You can go calculate it. I'm pretty sure it's worse. So it's probably a worse approximation than x equals 4, dx equals 0.01, because the dx is much larger here, at least in total size.